Hello, let's do this problem here, which is an application of the intermediate value problem. We're trying to show that this polynomial has at least one zero on the interval from -1 to 1. So in other words, we're saying that there is a number c such that f of c equals 0. We're not saying we can find that. Maybe someone can find a number, but we're not. We're just going to show that one exists. So this is an application of the the intermediate value theorem, and what we do is we start off with steps here. The first one is that the function f is continuous on the interval from -1 to 1 because it is a polynomial. So we had a theorem that said that polynomials are continuous. Because it's a polynomial, it's continuous. So I just wanted to change the color so it pops out a little bit there. Purple. Okay, well, then what I'm going to do is I'm going to evaluate the function f at the endpoints. So I go back to this function f, right? It's shown above, and I copy and paste, except I leave a blank space wherever x was, and I put in the number -1. And so I get, I get that's -6, I believe. Could be, yeah, I think it is. Okay, and then f of 1, I just do the same thing, putting in 1 where x is. And this is 4 plus 1 plus 2 minus 1, which is +6. That's sort of interesting. Does sort of make me want to double check, make sure I didn't do it wrong. So you get the same thing for, oh, no, sorry. It's not, it's 4, yeah. I didn't think it would be the same number. The opposite. One's -6, the other one's +4. Okay, so let's see. Now my next statement is that we see that f of -1 is less than 0 and f of 1 is greater than 0. Therefore, there is a number c where c is between, c is an x value between -1 and 1, such that f of c is equal to 0 by the intermediate value theorem. Finish the proof. I think I can write more neatly. It's always, not always, but sometimes the trick is to write neatly and sort of quickly at the same time. But I think I can do that with practice. But sometimes I let it slide. I have some desire to express myself through my handwriting, I guess. Subconscious desire, maybe. But, all right, there we go. Let's put a box around this. That's the end of the problem. That's it, right? I mean, you have to make a statement that the function's continuous, because that's one of the requirements for the intermediate value theorem. The other one is the value, and it continuous on a closed interval, which means it's an interval that includes the endpoints. And then you evaluate those endpoints, and you see the one endpoint has a y value that's negative, the other one a y value that's positive. So the function's negative, and then it's positive. Like, at the beginning of the interval negative, and at the end of the interval positive. What happened? Somewhere between -1 and 1, the function's equal to 0, and we don't know where. You can even plot a few points, but anyway, we don't know where the function's equal to 0. But it goes from negative and then to positive. So somewhere along the way, it has to equal 0. It's not even really such a brilliant statement. It's pretty clear that should happen. And you can, I don't want to start sketching the graph, but ultimately, more or less, you're down below at -1, -6, and then you're up above here at 1, 4, and it looks like I'm not even trying to do those to scale. Maybe I'll try a little harder. Okay, say this is 1, 4. Somewhere along the way, the function's 0. I don't know where. Here, but somewhere it's equal to 0. It goes from negative to positive. I don't know where. But that changes. But I know it changes somewhere. You can narrow the interval from -1 to 1 to, say, from 0 to 1. Because when x equals 0, you can see it's -1. So you can keep narrowing the interval and get a better estimate for where that value of c is. But somewhere in between there, between 0 and 1. Okay, so that finishes that